hydroboration-oxidation of alkynes. If we take an alkyne and treat it to similar hydroboration-oxidation conditions as we saw for the hydroboration-oxidation of an alkene, we will get a similar reaction. So what we will end up getting is we will form the anti-Markovnikov product. And specifically, we will see the anti-Markovnikov addition of water. So before we draw that product, I just want to look at the reagents. For the hydroboration oxidation of an alkene, we typically use borane BH3. For alkynes, we tend to use similar boron reagents, but ones that are a little bit bulkier. So we replace 2 of the hydrogens with R groups, which just means they can be any carbon group. And typically we pick some groups that have a lot of steric hindrance. So one common reagent is dicyanylborane. Another common reagent is this bicyclic system, 9-boro-bicyclo 3.3.1 nonane, which is a mouthful, so we give this the abbreviation 9BBN. So if you see 9BBN or you see dicyanylborane or any other boron reagent, it's going to do the same reaction with an alkyne. So that would be the anti-Markovnikov addition of water. So let's draw the product of the anti-Markovnikov addition of water. So numbering the carbon chain, anti-Markovnikov addition would mean that instead of the hydrogen going to the least substituted carbon atom, that it would go to the more substituted carbon atom 2, putting the alcohol on carbon 1. So there is the alcohol on carbon 1. And we can also show the hydrogen on carbon 2. So this product that we've just shown is an intermediate in this reaction. It is a molecule where you have an alkene and an alcohol on the same carbon. So this is known as an enol. So this is an intermediate. Enols are not stable. So what will happen to this enol is it will immediately tautomerize to move the alkene to be, or the double bond to be in between the carbon and the oxygen, which, since this is at the end of the chain, means that the overall product will be an aldehyde. So let's look at the mechanism of this tautomerization. And this is taking place after the oxidation step. So we are in aqueous base. So we want to look at the enol to carbonyl form tautomerization in basic conditions, and we will draw the mechanism for that. So here is the enol, and I've highlighted the bond between the oxygen and the hydrogen that we need to break. If we are doing this reaction in base solution, which we know from the sodium hydroxide, we will do a deprotonation first. So the sodium hydroxide is a base, and it will remove this proton. Giving us an enolate ion. This enolate ion is a base and it can get protonated. If we were to protonate on the oxygen, we would simply go back to the enol that we started with. Instead, we are going to push electrons through and protonate on this carbon of the alkene. So if we are an aqueous base, the base that we have is hydroxide. The conjugate acid of hydroxide, which is water, is the acid that we have available to us. So here is a water molecule. And so we will start by pushing these electrons down to form a carbonyl. That's how we get our carbon-oxygen double bond. And then we will protonate on this carbon atom by having that pi bond attack the hydrogen of water. And this gives us the aldehyde product.